Welcome back, and now what I am going to do is I will start from the previous talk where I had obtained an expression for delta rho, that is the change in charge density due to the perturbation of one particular wave vector and one particular frequency on a free electron gas. And now what I am going to say is that this charge density delta rho is going to give rise to a potential let me say phi q, and as dictated by the Poisson equation. And Poisson's equation is what? We have del squared phi q, we have del squared phi q is equal to minus 4 pi e delta rho. So, that will actually give me phi of q. Assume that phi of q has the same phase and wave vector, that is same q, the response is also at the same this spatial wavelength as the perturbation, and also has the same temporal behavior. So, if I use this, I can say that I will say phi of r comma t, I am actually saying is equal to phi of q e to the I q dot r e to the I omega t e to the alpha t. So, if I use that, then I put the delta rho into the just one component. I am only going to put one component. I will not put the complex conjugate. If I do not put the because it will follow automatically. So, what will happen is that I will get del squared phi q will be phi of q minus q squared phi of q, because you have a del squared phi q. So, this del squared phi q will give me minus q squared phi q, and e to the I q dot r and e to the I omega t and e to the alpha t will cancel on both the sides, and what I will get on the right hand side is minus 4 pi e squared times u of q sigma over k f naught k minus f naught k plus q divided by E of k minus E of k plus q plus h cross omega minus I h cross alpha. So, this is what we will get, but of course, you know very well that phi of q should be actually should be the self consistent potential That means the effective potential that is there, which is going to create the charge density, must be the solution also of the Poisson equation. So, which means that I must have the following, that is the perturbation, if the actual perturbation that you apply, the actual perturbation should be some V of q. And this gives rise to u of q, which is equal to V of q plus phi of q, okay. Or if I were to, and V of q, V of r comma t V of r comma t we assume has the same spatial and temporal dependence as a resultant, which is u q r of t and v q r of t. So, this will be equal to v q times e to the I q dot r e to the I omega t e to the alpha t. So, if you have this, u q is equal to v of q plus 4 pi e squared by q squared, because times sigma over all the occupied over all the states f naught k minus f naught k plus q divided by E k minus E k plus q plus h cross omega minus I h cross alpha, this times u of q. Right. So, this is the expression that I have taken. Okay. So, if I solve for u of q and write it as u of q is equal to the applied potential V of q divided by epsilon q comma omega, which is actually a dielectric constant, then I have an expression for epsilon q comma omega. All these are vectors. So, epsilon q comma omega, I have the expression 1 plus 4 pi e squared by q squared sigma over k f naught k minus f naught k plus q divided by E of k minus E of k plus q minus h cross omega plus I h cross alpha. So, this expression for dielectric constant is known as Lindhardt's expression. For the dielectric constant. In general, we can write down, for example, that if you have applied potential V of r t, which is actually given by all possible spatial and temporal oscillations of the charges, which is with amplitude v q comma omega, which is given by e to the I q dot r e to the I omega t dq d omega, then u of r t u of r comma t will be of the form double integral v of q comma omega divided by epsilon q comma omega e to the I q dot r t e to the I q dot r e to the I omega t dq dt and dq d omega, sorry. So, you see that this is a general expression for a spatial and for a non-uniform time varying perturbation electric field that you have applied on the free electron gas or in general on a system. So, this is the expression that we have. Now, let us see how we can actually simplify the expression for this dielectric constant that we have. So, what I can do is I have this epsilon k plus q minus epsilon k. I can do a Taylor series expansion and I can write it as q dot grad k E k. And similarly, I can write down f of k plus q minus f of k as equal to q dot del f by del E times delta k E k. So, if we substitute this, then what we will get for epsilon q comma 0 is the expression 1 plus 4 pi E squared by q squared times integral q dot grad k E of k divided by q dot grad k E of k times minus delta f naught by delta E times n of E d. N of E is the density of states. So, we can actually write it as epsilon q comma 0 is equal to 1 plus 4 pi E squared by q squared integral minus delta f naught by delta E n of E d. We know that the Fermi-Dirac distribution function f naught of E has a Heaviside step function or the theta function form behavior, that is at t is equal to 0 k you have this is the energy epsilon f, and this is f of E, and you see that f of E has a sharp, so f of E has a very sharp fall, and because of that del f by del E will be something like this. Or del f by del E is actually, this is at finite temperature. So, at finite temperatures you will have something that goes down like this, and you will have a width to the peak at the finite temperature. I think let me draw it again. That is EF. Okay. So, because of that I can say that integral minus delta f naught by delta E n E d E is actually n of E f, which is the density of states at the Fermi level. So, I get the expression for my dielectric constant epsilon q comma 0 as 1 plus lambda squared by q squared, and lambda squared is equal to 4 pi E squared times the density of states at the Fermi surface. So, lambda is like a screening length, okay. Lambda inverse is like screening length, is screening length, which is like the Debye-Hückel screening length. Okay. Now, we can do a little more manipulations in order to get some more physical insights into this dielectric expression. So, what we will do is the following. We can, let us do a Thomas Fermi approximation. approximation to get the change in charge density due to the potential. Due to applied potential. So, what we are saying is that if you have a free electron gas, okay, at the energy EF, so I am putting energy axis here and the occupancy on the right side. Okay, now supposing I put a potential, okay, let us think of an attractive potential. This is an attractive potential. Then what happens is the system must have a, at equilibrium we have the same Fermi energy, that is at equilibrium Fermi energy is the same at all places in the sample. The same over the entire sample. So, which means that some electrons should flow in from there outside into the potential, so that you have the same highest occupied state for the impurity. The energy of the highest occupied state of the impurity must be the same as the Fermi energy. So, if this should happen, what we expect is the following, that is, if U of r is a potential, then we have to remove a charge density which is equivalent to, or flow in a charge density if it is attractive, or remove a charge density if it is repulsive, which is actually given by rho of r, that you should get is NEF U of r into minus E. So, if you did that, what you will get is the following: del squared phi, which is the potential due to the charge disturbance, is given by minus 4 pi E times minus E N E F U of r, or that is equal to 4 pi E squared N E F U of r, or equal to lambda squared U of r. So, this is phi of r, which is a spatial dependence. Now, what we can assume is that phi of r is not very different from U of r. Okay. So, this Thomas Fermi approximation is also something that is very similar to what is done in the de Broglie theory to get the Boltzmann-Poisson equation in electrochemistry, because what there you will do is that the charge density you will get is now decided by the Boltzmann distribution of the potential. Say for example, what happens there is you have a thermal distribution or a statistical distribution of charges. So, this is in Boltzmann-Poisson equation. So, there your charge density delta n of r is given by uniform charge density times e to the minus delta u of r divided by k T, and this you linearize. So, you will just write it as n naught times 1 minus or you just write it as delta n naught, this minus n naught. So, this you write it as nothing but n naught by k T e to the delta u of r So, here also we have actually shown how a thermal distribution gives rise to a charge density. In this case, it is a electric potential that gives rise to the charge density. Then there also the thermal distribution may be because of the potential energy U of r. So, because you will have E E times kBT by E times r divided by kBT. Okay. So, what we do is, so now what we have is del squared phi is equal to lambda squared U of r, and we assume that for the impurity, if we let us for the moment assume, we assume that for the impurities potential delta phi is equal to delta u. Okay, that means our phi of r is equal to u of r. Okay, if you assume that, then you can substitute this in the Poisson equation, then what you will get is the following. Then you get del squared u is equal to lambda squared u, and so u of r. So, if you assume the potential is spherically symmetric, it only depends upon the distance, and that is given by E squared upon r e to the minus lambda r. So, this shows that lambda is the screening length. And this is a screened Coulomb potential. Now, if you look at the Coulomb potential, V of r equal to E squared by r, then the Fourier component the Fourier transform of this V of q is equal to E squared by q squared, 4 pi E squared by q squared. This we have actually in a way calculated, because we got the Green's function for E squared upon r, and if you Fourier transform the Green's function, then you get E squared by q squared. So, this has a singularity at q equal to 0. Now, u of q is equal to V of q divided by epsilon of q. Okay. And epsilon of q is equal to 1 plus lambda squared by q squared. So, when I put the things together, then I will get u of q is equal to, for the Coulomb potential, 4 pi E squared by q squared into 1 upon 1 plus lambda squared by q squared, or that is equal to 4 pi E squared by q squared plus lambda squared. Okay. What you will see is the following, that is, the singularity in the Coulomb potential, the Fourier transform of the Coulomb potential, which is V of q, the singularity in V of q cancels the singularity in epsilon of q. So, you do not have a long range part which is large, long range part of the Coulomb potential which is large, but it will die down exponentially. Okay. So, that is what it means, because if you have the Coulomb potential which is 1 by r, then 1 by r has a long range tail, and 1 by r e to the minus lambda r will have an exponentially dropping tail. So, that is going to kill the singularity that you are going to have at q equal to 0 or r equal to infinity. Okay, so there is one thing that I am going to state without actually proving it, which is that if you take this epsilon q comma 0 is equal to 1 plus 4 pi e squared by q squared, let me write down the whole expression once more, times sigma over k f naught of k minus f naught k plus q divided by E of k plus q minus E of k plus I h cross alpha. We can replace summation over k by integration. And this integration has actually been done in many places. So, this integration, the integration for the free electron gas, you can find it in many places. One of the places that I find very nicely done, at least in two different ways actually, is the quantum theory of atomic structure volume 2 by Slater. So, let me write it down. The integration can be seen in detail in J.C. Slater quantum theory of atomic structure, volume 2, and it is in appendix 22. So, when you actually carry out the integration, you get a very interesting expression. The expression you get for epsilon q comma 0 is the following. For the static dielectric constant, you get the expression 1 plus 4 pi e squared by q squared into n by 2 n by divided by 2 by 3 the Fermi energy times 1/2 plus 4 kf squared minus q squared divided by 8 kf/q times ln 2 kf plus q divided by 2 kf minus q. So, we see that this has a singularity at q equal to 2 kf. So, in the next lecture what I will do is I will dwell a little more on the singularity and then tell you what are the consequences of this singularity, and I will also discuss a few other things related to this singularity, which is this singularity leads to what are called cone anomalies in vibrational spectra of solids and so forth. So, we will talk about those things in the next lecture. Until then, goodbye.